I want to start this by saying that everything you see on the screen right now was programmed by me. I wrote some code that is actually physically watching microphone signals and turning it into a visual you're seeing. So, if you've ever worked with some form of audio processing, you've probably seen something a bit like this top line here. And if you've ever listened to electronic music in the 2010s, you've probably seen something like that bottom line there. What are these lines actually telling you? I want to tell you briefly just about how microphones actually work. So, when you speak, when you make any sound really, you can clap your hands, you can just, I don't know, tap a water bottle on a desk, you can do anything you want really. You are creating sound waves, and sound waves physically are just ripples in the air. Like if you think of like moving your hand around in a bowl of water, or in a swimming pool, for instance, what you're doing is you're physically nudging water out of the way, and that causes it to cascade and hit other water and hit that water out of the way, and then that cascades and it causes this rippling effect that just causes, the ripples that you're familiar with. And you have those little spikes and you have those dips. And so when you have ripples in water, that's effectively just this system of pressure where you add pressure on one side of some medium like water, and then it's going to push on the water to the right of it, and then push on the water to the right of it, and move on, so forth. All that good stuff. So now, it's exactly the same principle with sound in the air. You have, when you're speaking, there's a set of muscles in your throat called the larynx that are physically vibrating and just nudging air around really quickly. And then that comes out of your mouth through a series of formants. The linguistics behind that is really interesting. And eventually escapes out into the sound, into the ether of just the air around us, and eventually hits your microphone. And now, in your microphone, there is physically a very small magnet that is just genuinely being wiggled around by all these air vibrations. Like, it's a very tiny magnet that, like, pretty much just whatever hits it, it's just going to wiggle around a little bit, just like that rippling water. If you think of, like, some little buoy on water that's just moving up and down with the waves, that's pretty much what a microphone is, but for the air. So all these little pressure waves are hitting your microphone, and then all the microphone really gets is that this magnet wiggles around. That generates an electric current, and it turns that electric current back into voltage that it then is able to put into what we call an analog to digital converter, a special kind of circuit that is able to take these fluctuating voltages, like just plain pure raw electricity, and turn it into a digital signal. And so the analog to digital converter is actually going to then take that signal and turn it into some sort of number that pretty much says where is the magnet at a particular point in time, or how fast is the magnet moving. Now we kind of get to these visuals. What your microphone actually hears, like the actual thing that it's recording, is the position of this magnet, more or less. It's a little complicated, but for the most part, it's just recording the position of the magnet. And it's doing this incredibly quickly because sound is incredibly fast. People speak at, give or take maybe 3,000 hertz or whatever. That's like 3,000 oscillations in the air per second. And so my particular microphone right now is actually recording at a rate of 44,000 oscillations per second. It's doing 44,000 samples every second, and it's doing at a sample interval of 1,102 samples. And so what you're seeing on this bottom chart is actually just the raw each sample as it's coming in. Is that the microphone physically, just in one batch of requests, the computer says, hey microphone, tell me what you're hearing right now. And the microphone says, well, the past 1,102 oscillations went like this. There were some cases where the air pushed against me. There were some cases where the air pulled back against me. And so if you actually look at the bottom graph, you're going to see kind of it just goes up a bit when the air pushes up against it, and it goes down a bit when the air pulls back. And so if you actually make like a proper tone, forgive my bad singing, but if you actually make like some sort of tone like something like I did this earlier. Hold on, how did I do it? There you go, that one. You can actually see that it makes this kind of like pattern, this oscillating pattern. It's not very clean. I'm sure there's a way to make it that so it works consistently, but like that waving up and downness that you're seeing is physically just the air pushes against it and then pulls back in a perfect sine wave. And so when you see people talk about sine waves, that's what they're actually talking about, is just physically the air moving against the magnet in the microphone and nudging it back and forth. And so that bottom one is just the most frequent thing, so you're not going to see any time. And then you just take that and you chain it together and you zoom out. And so that middle line is actually just zooming out just a little bit. You've probably figured that out by now by looking at the diagram. And so you kind of just see the sound going by really quickly. And then you zoom out of that one and you get something similar to what you see in a program like Audacity, where you get that chronological time that vaguely represents the volume, because as you're speaking, that's going to cause the air to physically move a lot more. And so what you're actually seeing in this top diagram is just how much total is the air wiggling. And then, of course, you can do all the fancy math like Fourier analysis and all that good stuff to figure out how do you take all that wiggliness and turn it into like signals that you can do. And you can do things like, okay, can we start figuring out what signals are consistent so that we can filter them out as background noise? But my goal here was just to explain what these diagrams actually mean, where you see in Audacity that big like thing that just moves along with time, and on the bottom one you have that whole EDM effect where it's just like it goes all wiggly and it wiggles more when there's more sound and it wiggles less when there's less sound. You know, there you go. There's your infodump.